In this video, we're going to look at how we calculate a Ka and then our neutralization reactions. We are going to predict products of a reaction between a strong acid and a strong base, and then we'll create or evaluate models of a reaction between strong acids and strong bases. So let's go ahead and talk about the concentration of H plus in strong acids. So if we had a question that was, what is the H plus in a 0.1 molar HCl solution? We can go ahead and kind of apply some of the stuff we used last unit in this equation. So we know that the concentration of the HCl is 0.1. Because this completely dissociates, that means the concentration of the H plus is 0.1 and the concentration of the Cl ions is 0.1. So the concentration of our H plus would be 0.10 molar. So any of our 6 strong acids, that's how we would be able to concentrate the H plus ion concentration. So let's go ahead and talk about how we would calculate the molarity of the H plus concentration in a weak acid. For that, we're going to have to use something called a Ka, which is going to be a standard value that I'm going to give you. And let's say we have this question, what is the H plus concentration of, what is the H plus in a 0.1 molar HF solution? So here I'm giving you the Ka, and that's going to come from a reference sheet. And we know that HF is a weak acid, so it only partially ionizes, which means there will be some of that HF splitting apart, but most of it's going to stay together as HF. So in that case, what we're going to do is we're going to say we know the concentration of HF is 0.10 molar minus X, because some of those ions dissociate. And H is going to be X, F is going to be X. And then we can write our Ka very similar to how we did our equilibrium expressions. So we're going to take the concentration of our products, and because there's no coefficients over here, there's going to be no superscripts, but if there was a 2 here, then a 2 would come up here, and then we're going to put that over the concentration of our reactant. And then we're going to go ahead and put the values we have. So I told you the Ka, and again, I got that from a reference table. So it's 6.8 times 10 to the negative 4 is going to equal, we said that the H and the F were both X's. So times X times X. And then we said the concentration of the HF is 0.10 minus X. Now this minus X is so small that we're just going to ignore it exists, okay? When we put it in, it just doesn't change our calculations. So to solve this, this up top becomes X squared. We're going to take this 6.8 times 10 to the negative 4th, multiply it by the 0.10, and then we're going to square root it or bring it to the 1/2 power. And when we do that, we get our X to equal 8.2 times 10 to the negative 3rd. And remember, this is a concentration, so we can put molarity there. This is our H plus concentration. And if we wanted to, we could actually find the pH. So we could do negative log of that number, 8.2 times 10 to the negative 3rd, and we would get a pH of 2.09. And now that's not what the question's asking, but that's kind of bringing in everything we've been going through this unit. Okay, let's look at another practice problem. HClO is a weak acid. And there's some information I forgot to put in this practice problem that you're going to need. You're going to need to know that the H plus concentration is 0.30 molar, and then the Ka of this acid is going to be 3.0 times 10 to the negative 8. So as we're going through this, we're going to do the same thing. We know that the HClO3 is 0.30 minus X, because a little bit of it dissociates. This is X, this is X. When we write our Ka, it's the products, H plus, ClO minus. There are no coefficients, so there's no superscripts. We're going to go ahead and put that over the reactant. And then we put our values in. So remember, this is a value I gave you, that 3.0 times 10 to the negative 8 is our Ka. I'm sorry, my stylus is having trouble here. And then we know that this is x and x. When we multiply those together, we get x squared. And then down below, it's the 0.30 minus x. But remember that x is so small, we can ignore it. We're going to take 3.0 times 10 to the negative 8, multiply it by 0.3, and then square root it. And we should get our H plus concentration to be 9.5 times 10 to the negative 5th. And again, if I wanted to find the pH, it would be negative log of that number, and my pH would be 4.02. Let's look at another practice problem. So we have H2S, and if we're looking at this, we know that it is a weak acid. I do give you the Ka. I forgot to give you the starting concentration of the H2S, so let's say that's 0.2 molar for the H2S. And then I want to show you something. Here, this is the first time we've had an acid with 2 hydrogens. H2S is diproduct, which means that we have 2 hydrogens in there. But we're actually only getting rid of one of the hydrogens here. So you're going to see on your Ka sheet H2S with a couple of different Kas. Make sure we're grabbing the right one, and when we go through some more practice in class, I'll show you what that looks like. So we go through the process just like we've always done. We're going to say that our H2S is 0.20 minus x, x, x. Our Ka is going to be the H plus, HS minus. There are no coefficients, so no superscripts, H2S. So then we put in our values, so 9.5 times 10 to the negative 8, and then that's x times x, which really gives us x squared, all over the 0.20 minus x. We ignore this because it's so small. Multiply the 9.8 times 10 to the negative 8 times 0.2, square root it, and when we do that, we should get our H plus concentration to be 1.4 times 10 to the negative 4th. That's molarity. If we did negative log of that, we could get our pH to be 3.9. We're going to go ahead and save this one. We're going to do this one as an in-class practice because I think you've gotten a couple of examples. So we'll do practice problem 3 as a warm-up when we see each other next. So now we're going to move away from the calculation side into a neutralization reaction. So when an acid and base in appropriate amounts are reacted together, they're actually going to produce salt and water. So that's great because we can mix our base and our acid together and create salt water, neutralize it, so in that way we're not having, or companies aren't having to pay for chemical waste. Salt is an ionic compound. It's the cation from the base and the anion from the acid. So as we look at this, it's really a double displacement or double replacement reaction. Your hydrogen is going to form with the OH, and that's going to create water. Now, it doesn't matter how many OHs are at the end or how many hydrogens are up front. It's always water. And then your cation is going to form with your anion, and if we do some mental math, Na is a +1, Cl is a -1, the charges cancel, we don't have to add any subscripts. And then once we've got all of that put into place, then we can go through and actually balance it. So as we go through, we have a total of 2 hydrogens, 1 oxygen, sodium, sodium, chlorine, chlorine. I don't actually have to add in any coefficients here. So this would be the complete reaction. We also have a chemical formula that we use to kind of calculate and quantify how much of that acid and how much of that base we need. So it's the molarity or concentration of the acid times the volume of the acid times the number of H's, molarity of the base, volume of the base, number of OHs. So let's look at a practice problem. It says how many milliliters of 0.5 molar HCl are needed to neutralize 45 milliliters of 1 molar NaOH. The other thing I forgot to mention is that when we're looking at the volume, the units don't matter as long as they're the same. So you can use milliliters, you can liters, it doesn't matter. So for this, we have 0.500 molar for the acid. We don't know the volume, we know there's 1 hydrogen. We know that the base has a concentration of 1. We know the volume's 45. And we know there's 1 OH. When we're taking our sig figs, we're going to take it off these initial measurements. So there's going to be 3 sig figs in our answer. We're going to multiply these 3 together, divide by 0.5, divide by 1, and your volume should be 90.0 milliliters. Let's go ahead and go through another quick practice problem. So this one we have 25 milliliters of 0.25 molar H2SO4, and we want to fully neutralize 30 milliliters of KOH. What's the molarity of the KOH? So we have the 0.25 concentration of the H2SO4. We have 25 milliliters of that, and there are actually 2 hydrogens in H2SO4. We don't know the concentration of the base that we're trying to solve for. We know that the volume is 30 milliliters and there is 1 OH. So we're going to go ahead and multiply these 2 together, divide by 30, and we'll get the concentration of the base to be 0.42 molar. We're going to go over 2 quick vocab terms. So our endpoint is the point at which the indicator used changes colors. For us, we're going to use phenolphthalein, and when it turns that light pink, that's going to be our end point, and that'll make a little bit more sense once we start our titrations. Our equivalence point is when we have the H plus ion from the acid and the OH ion from the base being equal. We have 2 different graphs that we're going to be looking at, and so what this graph is showing us is the pH compared to volume of NaOH added, and we're working with HCl and NaOH. So the pH is starting very, very low, okay? That pH is starting at about a 1, which is why we have that strong acid. When we have a strong acid and a strong base, our equivalence point is going to be at about a pH of 7. And this tells us how much of that NaOH is added to get to that point. So we're adding about 45 milliliters of this NaOH to equal out the 50 mils of that 0.1 molar HCl to create salt water. And then here's an example with a weak acid and a strong base. You can tell it's a weak acid because our pH is starting a lot higher. We also have a different equivalence point. Our equivalence point is maybe like an 8.5 for our pH. And again, what it shows is if I have 50 milliliters of that weak acid, it's going to actually take maybe about like 47 milliliters of my base to titrate that solution and to get my equivalence point. Here's an example of a strong acid weak base, and so here we can see that the pH is starting at a weak base. We're adding acid to it. Right here we can see there's about 25 milliliters of acid that's added to the base, and here is where we would be able to tell the pH. So maybe 1, 2, 3, 4.8, maybe it's a pH of 4.8. We're going to get a lot of practice with reading these graphs, but I wanted to kind of just show you how these changed based on the substances you're using to titrate. You're going to get a lot of practice with the titrations, with the calculations. So if you have any questions, make sure you're writing it down, and then we'll go over it when we see each other next.